The final point in sequence comparison or alignment is multiple sequence alignment. So you can have a full lecture about it, but the ideas will be quite distinct but also somewhat similar. So if you have understood pairwise sequence alignment, you will be able to pick up multiple sequence alignment on your own. But we wanted to give certain pointers so that you are able to follow it up. Okay. And why do we need to do multiple sequence alignment? So in fact, we are not interested in studying just how two species evolve. We are interested in studying how all the species evolve. So oftentimes you're working with multiple species, all the primates or all the different forms of flies, all the birds. We want to understand how sequences have evolved across more than two animals or more than two sequences, how they are evolving, right? And so that is kind of the biological motivation. The statistical motivation is that if you have a faint similarity or a statistically insignificant similarity between two sequences, if you keep seeing that in more and more sequences, then that gets more significance statistically, right? So two sequences may have some kind of chance alignment that will give them a good score, but then if you have 3, 4, 5 and all of them giving you a faint but consistent similarity in all of these across all of these sequences, then you get more and more confidence about that being a true biological similarity rather than a random spurious chance similarity. Okay, so that is the kind of statistical reason for looking at multiple alignments. Is in addition to telling us about how multiple species has evolved, it also allows you to work with sequences that are pairwise very faintly similar, but then that faint similarity is consistent if you keep on adding sequences. And so with even faint but consistent similarity across multiple sequences, you can learn more about these sequences and how evolutionarily distant sequences have evolved, okay, by looking at multiple sequences. And so instead of comparing primates to just humans, you may want to compare every possible sequenced animal to understand a better context of how evolution has acted upon. First problem we started with, where there is this NRP synthetase, and there are these three different A domains that make up three different amino acids, right? There also we had three sequences, so we need to do three-way alignment, right? Not two-way alignment. So given that motivation, how would you approach this problem? That is what we will spend shortly. So we have, let's see how this alignment graph will look like. So alignment graph for two sequences was a grid graph that could be drawn in 2D, right? And so an alignment graph for three sequences, you could generalize it to, it may look like a cubic graph, right? So you'll be able to draw it in 3D, where each dimension will correspond to one of the sequences, right? So that is a natural representation. Let's just look a bit carefully on how that is. So your alignment of three sequences, if you write it down this way, this looks like a 3-row matrix, but the alignment graph will be a 3D graph. So how do you convert this? How do you see the correspondence between all possible paths through this alignment graph and all possible alignments of this three represented by this 3-row matrix? Okay, the same way that we were showing that any alignment between two sequences corresponds to a path in a grid graph, right? A 2D grid graph. Again, we have to add weights to these edges in the alignment graph, or have to add some kind of scoring for each of these columns. So dash AA, what score should it get, right? And G dash dash, what score should it get? So we have to also have a scoring matrix that initially was a 5x5 for two sequences, but now we have three rows here, right? So the scoring matrix has to be 5x5x5. That also has to be a 3D matrix, right? And then generally the scoring matrix, you want it to score columns which are the same. Like for instance, we have AAA, they should have a very high score. And then certain other things, I guess there is this G dash dash, it should have some kind of a penalty because there are two deletions which are happening, right? So those are all the requirements. And how do you see that alignments are paths in 3D? So we are not going to go into it in very great detail, but we are going to come up with some kind of a simple coordinate naming scheme. Okay. Initially we had this 0, 0 to n, m, and then we had this grid graph, right? So all of this grid graph going for 2D alignment. For 3D alignment, we will have a 3-dimension and then 3 coordinates, and that coordinates will be named using the index using the number of symbols seen up to a given position. So if you have this kind of alignment, so this previous alignment here, right, has been written in this or a slightly different alignment has been written in this way, right? and then you have, and then you label them with the number of symbols seen till then. So here you have not used up any symbol, so that is 0. In the first sequence you have used up, you have read one symbol, that is 1. Here there is a dash, right? So that is some kind of an insertion in the other sequences, right? So you have 1, you have still only read A, so that is 1. You have now read T, so that is 2. Read G, so you have 3. Read C, you have 4. Okay. Similarly here. Here you start with a blank and then you are reading AAT, so it becomes 1, 2, 3. Here is a gap, so that stays at 3. You have C, so so that becomes 4. Okay, and similarly here you will have, let's just write it down, so that, so this will be 0, this will be 0, this will be 1, 2, 3, and 4. Right? Let's just see if that is indeed the case. Yeah, so you have 0, 0, 1, 2, 3, 4. Okay. Now you can see that if you take these indices 0, 0, 0, right? So if you take these indices 0, 0, 0, it goes to 1, 1, 0. From there it goes to 1, 2, 1. From there it goes to 2, 3, 2, and so on. That is the path in the 3D alignment graph, right? This is the 3D alignment graph. Instead of having 0, 0 to n comma m, right? You are now having 0, 0, 0 to n, m, and q, if n, m, and q are the lengths of the 3 sequences. Okay, so this is what these graphs look like. This is 0, 0 to n comma m, and then you have 0, 0, 0 to all these n comma m comma q. Okay, and then instead of 3 edges which are coming in, now you have more edges which are coming in, right? 1, 2, 3, 4, 5, 6, 7 edges which are coming in this particular graph, right? And then that just simply comes from changing each of these I, j, and k to I minus 1, j minus 1, and k minus 1 in order, right? Actually, it should be 6, right? 1, 2, 3, 4, 5, 6, 7. Oh, you can also change 2 at a time. Yes, yes, yes. So this is just 3, choose 2. Yes, yes. Yeah. So there are 8 such possibilities, and ijk is ignored. So you have 7 edges which are coming in. Here you have 3 edges which are coming in. Okay, this is 3, this is 7. And the dynamic programming will then also have 7 quantities that you're taking the maximum of. Initially, we only had 3 quantities, right? So you have all possible ways in which you can change ijk to I minus 1, j minus 1, and k minus 1. Okay. So this is coming in from I minus 1, j minus 1, k minus 1, I minus 1, j minus 1, k, and so on. Okay. Wherever you are going from I to I minus 1, you're consuming this letter and you're consuming the wj, you're consuming the third sequence uk, right? So you will have this delta of all of this, where delta is your 3D scoring matrix, this 5 cross 5 cross 5 for DNA that I talked about. Okay. So, so this is the natural extension of 2D or pairwise alignment to 3D or this multiple 3-way alignment, right? But there's a problem with this, right? So if you have 3 sequences, then your runtime is going to be proportional to n cube, each of length n. So it's going to be 7 times n cube, because you have 7 of these that you have to compute, and there are n cube such nodes, right? In this particular cube, there are n cubed number of vertices in this cube, right? So for a k-way alignment, you will have n to the k nodes, right? And you will have 2 to the k minus 1 incoming edges, right? Because each of the I, j, k, etc. can become I or I minus 1, right? And excluding 1, which is the I, j, k, the current node. And the runtime is going to be order of 2 to the k, n to the k. And whenever we have n to the k, where k can be quite large, we want to align all the primates, and k is easily running in tens or 20s, or if you want to look at all the species, hundreds of species, then this is impossible to run on current day computers, right? And soon you will run more than the number of atoms in the universe. So that's not possible. So people will resort to kind of heuristics, right? So we want to mention a couple of heuristics that that people attempt. One idea is that every multiple alignment induces pairwise alignments. So can we do pairwise alignment? We do 2 sequences at a time, and then somehow use that to piece together a larger multiple alignment, right? So that is something that you could do. And so there, the question then is given a arbitrary, given a set of arbitrary pairwise alignments, can we construct a multiple alignment that induces them, right? So each of these pairwise alignment may not exactly be consistent with each other, but how do you merge different pairwise alignments to get a single consistent multiple alignment, right? That is one question. And that can be answered using something called a profile representation of multiple alignment. And a profile representation, you have a multiple alignment, and each of these columns you just represent it using the frequency of AC, GT, and dash in that particular column, right? So you have this particular column where all of them are G, so you just put G1 is 1, fraction 1, everything else AC, T, and dash are 0, right? In this other case, you have CCC is 3, so that is like 0.6, then you have T, and then you have a dash, so those are T and dash are 0.2 and 0.2, right? So you just convert this multiple sequence alignment MSA into a profile, looking at it one column at a time, okay? And now to get this kind of merging, to address this merging problem, instead of aligning a sequence against a sequence, if we are able to align a profile against a profile or a sequence against a profile, we will be able to solve that problem, okay? Because each of these pairwise alignments, you can represent it as a profile, and then we are going to then align a profile against a profile, or if there is only one sequence and there are odd number of sequences and there is one more sequence, we can align a sequence against a profile, okay? That way we will be able to merge different alignments into one alignment, okay? Whether it is pairwise alignment into one alignment or different multiple alignments into one alignments. So those are the two questions here. Can we align a sequence against a profile? Can we align a profile against a profile? If we are able to do that, we will be able to merge alignments for a smaller subset of sequences into one single alignment that covers all of the input sequences, okay? That is a strategy that we can use. And if you have that algorithm, right, so like I said, I'm not going to give all the details of multiple sequence alignment. It will be another session in itself. But if you have such subroutines for aligning a sequence against a profile or a profile against a profile, then you can choose the most similar sequences, right, combine them into a profile, and then you can reduce the alignment of k sequences into an alignment of k minus 2 sequences and one profile, right? So you have all these sequences 1, 2, etc. to k. You look at the two most similar sequences, maybe these are the two, rest are the k minus 2, right? So then you have basically one profile, and then you have k minus 2 sequences. So that is what you have reduced the problem to. You had k sequences, now you have one profile combining two sequences, and then you have k minus 2 sequences. Then you can again look into all of these, and then you can look at, let's say I call all of them as meta sequences, so they can be either sequences or profiles. So you have k minus 1 of them. Again, I will look at which pair of them are the closest, and then I will start merging them. And it's something similar to hierarchical clustering. If you have seen before, you have a set of k objects, you find the two closest objects and represent them using their average, and then you have k minus 1 object, then you look at the next closest pair of objects, you again reduce it to k minus 2, and you keep proceeding, okay? This is the iterative formulation. This is an example here. You have sequences which are these 4 sequences, right? You can do 6 pairwise alignments, right? So 4 choose 2 is 6, all pairs of these 4 objects, right? And then for each one of them you get a score of 2. So S2 and S4 gives you a score of 2, the best alignment, S1 and S2 score of 1, and so on. So then S2 and S4 are the closest sequences. Then I can merge them into a profile, and then I'll have that profile and all the other sequences, right? So S2 and S4 has been merged into one profile. So now I have the profile and 2 sequences, and then I can iterate. Okay, this is the profile of S2 and 4, right, represented using this T and A and C, right? In this particular case, all the others are exactly the same. Now we have this new set of 3 sequences to align, right? So T and A and C being this representation of these letters, and then you can keep iterating, right, to reduce it down into 2 sequences, and then finally down to 1 sequence, okay, or sequences slash profile, I will say, 2 objects and down to 1 object, and that final object will be your multiple sequence alignment, or the profile corresponding to that multiple sequence alignment. Okay, this is one strategy to build a multiple sequence alignment, a small subset of sequences at a time, but merging the most similar sequences or most similar sequence and profiles at each step. Okay. So this concludes the topic of sequence alignment and multiple sequence alignment. And there is one particular topic that we have skipped for now. If there is time, we will look into it later, which is the statistics of these sequence alignments. We will probably post resources on that, and then you can look into those resources on if you have two random sequences, what is the best alignment score you can get out of spurious fit. Okay, and so thanks for coming. We'll just stop here.